Okay, thank you very much. Thanks for the opportunity to talk. I try to talk a little bit about the paper itself. So here's a snapshot of this famous. So it's a 60-page paper, and it's I think quite a revolutionary paper. Actually, I tried to like dive into it when I started writing my chapter, and I've made a few discoveries that I'd like to share with you. Um, so the first thing is that, as I don't know, maybe most of you know, I don't know, this so as the title indicates, actually it's a collaboration between a mathematician and a botanist, John Christopher Willis, who had measured the number of the species per genus in families of I think of plants, of vascular plants in Sri Lanka. And um, and he had a theory about it, about the fact that actually what led to this variation is due to the relation between age and area. And so here's as you can see, a citation of Yule's paper. um, the view that specific differences arise not cumulatively by the natural selection of slight favorable variations, but at once per saltum as mutations. Okay, so he sees the appearance of new species and of new genera as mutations. On this view, a new form must necessarily occupy a small area, and the required correlation between age and area follows at once. And so he made this thought precise, but by devising a model, right? And so the here's a picture of actually what the model is about. It's not just the pure birth process. It's a pure birth process of pure birth processes. And so I think that's pretty amazing for the time. So you see here on the left the primordial genus, which starts at time zero with one single species, and then from then on you iterate this process. Each genus gives birth at rate g, and upon birth the daughter genus, so there's always a mother that continuates, and a new genus, the daughter genus, that starts with one single species. As you can see here, you see that the black lines here are species, and within each genus independently, species give birth at rate s. Okay, so you have two parameters, g for the birth rate of genera, and s for the birth rate of species. Okay, so you have derived genera, a lot of derived genera, and one primordial genus. Okay. So what Yule actually got as results in this paper, I will talk about mathematical results. The first one, as Simon showed, is that this pure birth process that I will call YT, Y like Yule, of course, this pure birth process has when you fix the age of the process, let's say small a, has a geometric distribution with parameter exponential minus SA. All right. And so when you apply this to the genera, of course, the expectation of the number of genera at time t is exponential GT, right? Because now the parameter is G and not S for genera. And then what he also derives is that if you call now NT of A, dA, the number of genera at time t with age in the infinitesimal interval A plus dA, he showed that by a differential equation argument that the expectation of this number is G exponential G times T minus A, right? And so then he defines, actually, he doesn't do that like very accurately, but actually that's what he's doing. If you define ny of t, the ratio, it's really a ratio of expectations of the expected number of genera with n species by the expected number of genera. So you can see here the mathematical formula for this, disintegrated or integrated over the age. Then you get this formula, right? And so that's the formula. I think that maybe Simon showed it. It's supposed to be the let's say the frequency of genera with n species, right? But it's really a ratio of expectations. And so then you can compute it's complicated to compute this integral, but when you let t go to infinity, then you can compute it, and you get this formula for f and y, and f and y is actually known as the Yule or Yule-Simon distribution. I will say a word about that later. And so it's not difficult to show that this distribution has a heavy tail, a power law tail, with exponent alpha plus 1, right, where alpha is g over s. And here you think of g over s as being smaller than 1 because the speed at which genera regenerate is smaller, of course, than the speed at which species regenerate. And so I started this writing this chapter with the following questions. Is FNY also the law of the size of a randomly chosen genus, and not only a ratio of expectations? If yes, what is the structure of correlations of sizes among genera in Yule's model? And what happens if you add extinctions? Okay, and when species go extinct, can you try to compute how the sizes and ages of genera co-vary with the phylogeny? Okay, because here there's no tree, as I will emphasize. So then, like a small slide just to show you that Yule didn't only compute these distributions. He fitted his model to a data on count distributions in these two families of beetles and the legume family. And he says, I really love this bit. He says, the resulting points on a log-log scale, the resulting points in any actual case run rather irregularly but fairly closely round a straight line, usually up to genera of 30 species or so, that the agreement between observation and calculation is throughout extraordinarily close. It is in fact better than one has any right to expect. Actually, if you go to the Wikipedia page, you see that when you like take the whole families of let's say of plants, for example, you still get like this quite a very good agreement with the prediction of Yule's model. So now so after what I did is I tried to have a look at who cited Yule. Who cites Yule 1925? Actually, so as of today, we have approximately 2,600 references to the paper. And actually, if you do that search, you will see that they fall into very well differentiated categories. The first category is the one that we are interested in, is random tree models for species phylogenies in population biology, macroevolution, phylogenetics, and mathematics applied to these fields. But there's also a whole literature on power distributions as describing real life distributions, frequency distribution, illustrating the so-called rich get richer effect or preferential attachment. Why is it called preferential attachment? Because each time a genera undergoes a new speciation, the probability, the rate at which it undergoes a speciation is proportional to the number of species it contains, right? So if you discretize the time in the Yule model, what you get is really a system of urns where the number of urns grows and the number of balls in each urn grows also, but with this kind of preferential attachment phenomenon. And so actually, between 1925 and 1945, 50, even 50, there are very few citations to Yule. You can check, and I asked science historians, and they say that the references that you can see, that you can investigate on the web are quite good, because the vast majority of works in science in the beginning of the 20th century have been digitalized, right? So the data are here. And so what you see is that actually the extreme majority of these 200 of these 2,600 references are due to these two papers. So the second paper, I will start with the second paper. The second paper is the paper by Herbert Simon, who rediscovered the paper by Yule, who actually got what is called the Nobel Prize in economics. And after whose name the distribution is now known, right? It's called the Yule-Simon distribution. And the other paper is this paper by David Kendall, the well-known statistician who was actually the PhD advisor of John Kingman. and who has written a lot on birth-death processes in biology. And actually, this paper doesn't cite Yule. But this paper is also an account of a symposium taking place in 1948 at the Royal Statistical Society. And I think I should recommend the reading of this paper for the math, but also for the account of the symposium. And so here it goes. So I read this excerpt from this account of Kendall, which says, which speaks about surprises in the literature, papers that were concealed in the literature. Okay, so it's not a recent thing, right? So it has always existed. And he says, I'm sure there must be many more references to early work which I have omitted in ignorance. I regret none more than that to a paper of Mr. Yule containing a derivation of what has since been called the Furry process. So that's why people call the pure birth process the Yule-Furry process. Actually, if you look at the first three papers that introduce birth-death processes, they do not cite Yule. So the first one is a work in particle physics. The second one is a work by Feller in German that introduces the birth-death process. And the third one is a work by Kendall on the birth-death process with time inhomogeneous rates that is quite celebrated. And actually, after the account of the symposium, you can see that the rediscovery of Yule's paper has led to a spread of citations. And I only cite like the three first works I showed that cite Yule's model, Yule's paper. And so you see that the first papers that cite his work start in 1951. And unfortunately, 1951 is exactly the date of death of Yule. So that's kind of a sad story. I won't go through the details of these citations, but all these papers have some interest, despite the fact that one of them is written by Darwin in 1953. So the modernity of Yule's paper, as I mentioned in the title, for me goes as follows. The first thing is that you see in his paper that he talks about rates. He talks about rates as we would talk about rates today, as Feller actually introduced them when he discovered Markov chains in continuous time. So it's only in the 40s that really the solutions to the Chapman-Kolmogorov equations were found by Feller, despite some already ongoing progress on Brownian motion and diffusions, weirdly enough. So it's only in the 40s that Markov chains in continuous time were introduced. Another very modern aspect of this paper is model fitting on abundance distribution data. Of course, this was one of the first papers that did that, but of course, a very well-known paper did that 20 years later, and Simon talked about it. A paper by Fisher, Corbett, and Williams. And it's also a paper on a neutral model of evolution, right? So it's a neutral model of macroevolution that has I think like pretty much lost its attraction, its attractivity for 40 years. And then, as you all know, there has been a lot of revival of these neutral theories in evolution, and also in macroevolution, as these papers here show. And the last and most important thing is trees, right? We always say Yule trees. So did Yule introduce the trees? Actually, he didn't. If you go back to this excerpt of by Kendall that I talked about earlier, I had I had truncated the citation here. And what Kendall says of the other new work which has appeared since my paper was written, the most important appears to be that of Richard Otter, which is cited here, who has linked up the problems of the growth and extinction of populations with the combinatorial theory of trees. So it's really a paper about trees, mathematical random trees. And so as Kendall points out, this was being discussed a few years after Galton there proposed his surname problem. And so the same thing happened, let's say 50 years ago. There was a kind of a anniversary, a 100 years anniversary of Galton's work. And he says the near century which has had to elapse for these two topics, random trees and process that describe the growth of populations to become reunited. So if Yule didn't introduce trees, so what did he do? So actually, if you browse through his paper, you see that he never mentions the words tree or genealogy or lineage. He never even mentions the words birth or offspring. He says a species throws a mutation. And so when he considers that the total mutation rate of a genus is n times s, so n is the number of species in the genus and s the mutation rate, actually, we can wonder whether he knew that it was equivalent to saying that each species gives birth at rate s independently. He actually just counted the number of new species or new mutations. But there was no, I think in his mind, there was no genealogy, let's say, underlying. So let's go back to this Yule tree of trees. Let's say now Yule tree of trees, with bearing in mind that actually he didn't have this picture in mind. And so remember my first question. So here, when you draw this picture where you orient your tree from left to right, just like the mother to daughter arrows here. So genus 0 here is the primordial genus, and then you can label the genera in this order, 1, 2, 3, 4, 5. And then here the AIs are the ages of all the species, okay? And as you see here clearly on this picture, these AIs are exponential and independent, right? And so what we suspect here is that actually the F and Y, this law here, is also the law of the size of randomly chosen genus. Actually, we can show that the sequence of ages and size of genera, so if you call AI the age of species I and SI the number of species it contains, the size of it, sorry, ages and sizes of genera, then you can show that it forms a sequence of independent random pairs. Okay, and as T gets large, you can show that the age A of a genus follows the exponential distribution, as was clear from the picture, from the previous picture. And you can show that of course, that the probability of the size equal to n, conditional on the age, is just the law of the Yule process at time A. Okay, so what you get is indeed that F and Y is the joint law of age and size integrated over the age. And then you can do whatever, like compute, for example, the expectation of A conditional on S. There's a lot of like simple formula that you can get. So now if you add extinctions, what happens? So assume that in each genus, the number of species follows the Markov process X, which may or may not be a birth-death process, right? Whatever Markov process, for which 0 is absorbing. So whenever the number of species in a genus hits 0, it's over, and then the genus is declared extinct. Okay, and when it is extinct, it cannot give birth. So here, the number of genera is not Markovian because there's no reason why the lifetime of a genus, which is the extinction time of the number of species, might be exponential. And so now there's a difference between the age here of species I, here species 2, and the coalescence time here, age 2 between 1 and 2. Okay, there's a difference between the age and the coalescence time. But we keep the same property. In the presence of extinctions of genera are prescribed by their size, right? XT. And XT is a non-heritable trait. It's reset at 1 whenever you start a new genus. And so we can use coalescent point process theory to show the following theorem, that now if you look not only at ages and sizes, but also at coalescence times, these triples here are again independent, and they're distributed as a triple HAS, where conditional on A, on the age, the coalescence time and the number of species are independent. The joint law of H and A is semi-explicit. I will try to write it in the paper, but of course, I won't bother you with that. And the law of the number of species of the size of the genus, conditional on its age, is the probability that XA is equal to K, conditional on being non-zero. Okay. So then you can apply this to any Markov process X. And funnily enough, if R is the exponential growth rate of the number of genera, then you can write this relation here in a way which is similar to the one that we had earlier. So I will stop here and just mention a few perspectives. We can extend this framework to mass extinction events. Actually, even Yule mentioned this possibility, but mainly to emphasize the fact that he did not consider any selection mechanism. We could also try to work on a generalization of preferential attachment Ernst schemes, and Simon cited some of these papers here. And last, I will just say a word about the fact that trees within trees, which were kind of invented by Yule, but not really because he didn't know about trees, is following an explosion, of course, in the literature, both the biological literature and also recently the math literature. And I will thank you with that. Thank you very much.